So here's our continuation of protein structure. Now, we're going to begin this conversation with our second major secondary structure, that being the beta sheet or beta sheets. These are an extended conformation. The other secondary structure that we've previously talked about are the alpha helices. Now, this is rooted back to some of the conclusions and observations made by William Asbury in terms of the stretches of wool fibers. And one of the things that's very important for you to understand about the beta sheets is that they form basically two major structures. They are anti-parallel or they are parallel. Now, an anti-parallel beta sheet is a strand that, let's go ahead and imagine that this is our N termini. It's going to go in the N to C direction, so this is the C termini, and then it's going to loop back in on itself, making this the N termini and this the C termini. A parallel beta sheet, by contrast, would be, here's our N termini to our C termini. Now this is going to go in a slightly different direction because it's going to kind of loop down and swing back, making this the N to C terminal direction. Now, what's important to know about the beta sheets is that beta sheets can form from neighboring polypeptide chains. I like to draw this though because I think that it shows a depiction of where those different strands align with one another. Now, with that in mind, this is our parallel and our anti-parallel beta sheets. Now, our anti-parallel beta sheets, one of the things that I want you to observe about this is that here's my hydrogen bonds. The anti-parallel nomenclature is related to our strands. They are going N to C, N to C. So they are opposite. They are in an anti-configuration or direction. My hydrogen bonds that connect all those strands of our beta sheets, however, those are completely parallel to one another. But more important than that is that these are strands that are kind of up and down with one another. These are strands that are totally aligned with one another. And beyond that, these are like, so you can just describe them simply as they're straight up and down compared to our parallel beta sheets where they're at an angle. Now, the significance of this is that these angled beta sheets, or sorry, these angled hydrogen bonds are a little bit longer. They're kind of stretched out. Now, the significance is that these anti-parallel beta sheets are stronger than our anti-parallel beta sheets. Now, different types of beta sheets can exist. You can have a mixture of them. You could have a beta sheet that's exclusively parallel or an exclusively anti-parallel beta sheets. Okay, now large beta sheet structures exhibit a right-hand twist to them. Connections between the strands can either be simple or they can be complex. They can be one type, they can be parallel only, they can be parallel and anti-parallel. That would be a more complex version. They can be simple loops, or they can contain additional secondary structures such as alpha helices. Now, what we kind of alluded to, or what we mentioned a little bit when we were talking about our alpha helix, was our amino acid structures. We didn't get into it too much, but we really kind of mentioned them as, hey, they don't play that big of a role. Well, amino acid side chains should cover and protect the backbone hydrogen bonds forming that secondary structure. Now, the types of interactions are important. There can be charge repulsion, favorable ionic interactions, and the location of all of these residues is very important. Now, what's significant about this is our alpha helices. All of our amino acid residues are protruding outward from our helical structure. When it comes to specific amino acids and formation of an alpha helix or a beta sheet or something of that nature, there is a preference. Certain amino acids give way to the formation of an alpha helix, and certain amino acids give way to the formation of a beta sheet. Now, the coil of an alpha helix constrains space between adjacent and vertical amino acids. We alluded to and we looked at the I to I plus 4 hydrogen bonding pattern. Sometimes there are helices that are a little bit tighter in that they'll have an I to an I plus 3 rotation. Now, alpha helices typically are going to prefer smaller and less bulky amino acids. In addition to that, they'll prefer extended non-beta branched amino acids. So something like arginine as opposed to an isoleucine. So think about what are our beta branched amino acids. Well, our beta branched, if you think about N, C, C, this is our carboxylic acid right here. That would mean this is our alpha carbon. This is our beta carbon. And if you have H3C, CH3, like you have in valine, that's considered a beta branched amino acid. There's also a preference for amino acids that produce a favorable ionic interaction or favorable ionic interactions. When it comes to specific amino acids that are favored for the formation of alpha helix, we have alanine, glutamic acid, methionine, leucine, phenylalanine, glutamine, histidine, lysine, and arginine. When it comes to beta sheets, the extended structure of beta sheets leaves the maximum space for the amino acid side chains. So large, bulky side chains are preferred to form beta sheet structures. Examples of large residues are tyrosine, tryptophan, phenylalanine, methionine. Methionine, when you think about that, it's not necessarily an enormous amino acid residue, but think about the atoms within that residue. There's a sulfur atom there. So that is a sulfur followed by a methyl group. So it's a slightly larger amino acid. Bulky and awkward due to beta branched carbon are preferred for beta sheets, so isoleucine, valine, and threonine, because those are not preferred in the formation of alpha helix. A large sulfur atom on a beta carbon, like is the case with cysteine. Now, all of these amino acids are going to be kind of preferred to be in an alpha helix, are going to be spread out there on the exterior of our helix. Both sheets and helices can be amphipathic and amphiphilic. They can have one polar and one non-polar trace to them. Remember that there's a 7 pseudo residue repeat in alpha helices, so this is that I to I plus 3, so this would be residue I to I plus 3, which would be 4. And so this is kind of that repeat pattern that we have sometimes when it comes to the formation of alpha helices. Now, those are all the residues that are important for or likely for the formation of an alpha helix and beta sheet. What I would strongly recommend that you know about these is I would recommend that you know the residues that are the kind of the rules or the general overview. That being that alpha helices have a preference for smaller, less bulky, extended non-beta branch residues, and those that give about favorable ionic interactions. And then your bulky and larger residues are preferred for beta sheets. Now, there are some residues that are, oh, this is likely to form this structure, but then there's other residues that are likely secondary structure breakers. So these are the disruptors. Now, one of them might be a little bit curious, like, oh, interesting, that being glycine. It's like, okay, got it, glycine. Well, glycine presents the problem or the challenge that it's entirely too flexible. This has a side chain hydrogen that's too small to protect the backbone. Proline is another amino acid residue that is a secondary structure breaker. Proline's a secondary structure breaker because it has the opposite problem for that of glycine. This is an amino acid that is too rigid. So it's the exact opposite problem as glycine. Glycine is too flexible, proline is too rigid. They're kind of at opposite ends of the same spectrum. Now, if you think about proline, I always like to go ahead and draw the side chain for proline, and that's going to be this right here. I think proline's a good one to remember, basically, that this bond right here, this is our N to C, that's our phi angle, that's going to be very restricted in proline, whereas other amino acids, it doesn't have that same restriction. So strong hydrogen bonding side chains compete directly with hydrogen bonding the backbone. Examples being asparagine and serine, aspartate to a lesser extent. So along those same lines, glutamine and glutamic acid, and even lower extent there. And likewise, threonine. Now, clusters of breakers give rise to regions known as loops or turns, which mark the boundaries of alpha helices and beta sheets and serve to link up secondary structure segments. Tight turns, so this is within a secondary structure, there can be what's known as a tight turn. And this consists of 4 to 5 amino acids in a well-defined structure. It's not a repetitive movement like an alpha helix or a beta sheet, or repetitive sequence. This is in contrast to loops or random coils, which are completely non-repetitive and have no well-defined structure. So these have a specific well-defined structure. Beta turns allow the peptide chain to reverse direction. Here's an example of that in place. A beta turn, shown here, is broken into two different types. There's type 1 and there's type 2. And the way that I always kind of visualize this, I like to think about this as my N termini, and this is my C termini. Now, kind of a continuation of that is we have something that looks like this, where here's our part of our beta sheet that has formed there. Now, the difference between these two different turns, a carbonyl carbon on one residue is hydrogen bonded to the amide proton of a residue 3 residues away, which is what we see right here in our type 1 and our type 2. That has our I to I plus 3 pattern, similar to what we saw, or what I mentioned a little bit ago with respect to the alpha helix. Now, proline and glycine are two amino acids that are prevalent in these beta turns. Again, this is why they're kind of interesting, because they are typically secondary structure breakers, but in this case, their ability to break a secondary structure basically provides the ability for a secondary structure to form. Now, 10% of proline residues in proteins follow a cis peptide bond. So ultimately, what I want you to know about that is that proline and glycine are secondary structure breakers. Kind of their nature is to break the secondary structure, but that nature can kind of be harnessed to form those tight turns. Now, this right here, this figure right here, I always like to reference this and bring this up because it's very important due to the relationship it has to secondary structure prediction and basically where the world is when it comes to protein structure determination. Now, the way that I like to think about protein structure is I have a very simple understanding of it. I'm not a structural biologist really by any stretch of the imagination. But the way that I visualize it is if you know what something looks like, if you have a detailed understanding of, let's say, let's use a house as an example. Let's say that the house is similar to the protein. If you know what a house looks like from the exterior. You can describe it. You can say, oh, well, it's got, a yellow door. It's got a three-car garage. It's got five windows on the front, and then, that's the front of the house. Then you can go to another side and describe a little bit about it, but basically describe the entirety of the house, the exterior. Now, if you have that and you have the blueprints of the house, then you can piece those things together and you can say something like, well, if you wanted to make a meal, what you would want to do is you'd want to go in through the front door, walk 10 paces, and then turn left, walk 5 paces, and then you're in the kitchen. That's where you'd make a meal. Now, all of this is to say the better understanding of that you have of what something looks like, the more detailed your understanding of what something looks like, the better you understand it. And the same thing goes with proteins. For ages, people have been trying to figure out what do proteins look like. And we have techniques. We have um, NMR. That's There we go, NMR. We have X-ray crystallography. And these are methods and mechanisms that we can use to basically solve a structure and say, aha, here's this detailed picture that we have. But there's some drawbacks to that. Um, it takes, first and foremost, it's going to take, above all else, time. It's going to take time, and whenever you're doing protein structure determination, um, if you dedicate, 6 months to purifying a protein and solving its crystal structure, um, you might never get that protein structure. You might never get the entire protein structure resolved, in which case you've spent 6 months and, have you moved the field forward? Maybe a little bit, maybe not at all. So that time can be lost. It can be sunk. Now, that is important to consider because there's this alternative where you can use the field of bioinformatics. And you can solve or make a very good prediction about what a protein looks like based on its composition. Now, I bring all that up because this figure right here was a very important, or it comes from a paper back in the 1970s. And this paper basically set out to say, here's all the data that we have in the realm of protein structure prediction. We have all these secondary structures that have been resolved. And what we're going to do is we're going to use that information to basically um, say, well, we think that this secondary structure might be formed. So essentially, the authors of this paper, Chow and Fassman, what they did was they took all of the contemporary data and they looked at protein structures and they looked at secondary, like primary structure and secondary structure. And they went through all of the proteins that had an alpha helix. And they said, okay, well, this alpha helix has all these amino acids. And they basically said, okay, here's an alanine. And then after that is a histidine. And then after that is an arginine. And it's almost like they're keeping a tally. And they said, okay, alanine is there, histidine is there, arginine is there. Where is it? Arginine is there. And over time, what they came up with were scores that are referred to or known as propensity scores. These propensities were determined based on the statistical distribution of amino acids in alpha helices, beta sheets, and turns or loops using known structures. So they basically gave this statistical analysis that said, oh, well, if there's an alanine, there's this percent chance that that is going to be in an alpha helix. And came up with a scoring system ranging from 0 to 2, 2 being an amino acid that is most likely to be found in an alpha helix or a beta sheet, a propensity alpha or propensity beta. The higher the number, the more likely that amino acid is going to be found in one of those structures. And so if we look at an amino acid like alanine, alanine has a p sub alpha of 1.42. It has a p sub beta of 0.83. So it's likely to be found in an alpha helix, and it's less likely to be found in a beta sheet. Now, this is very powerful because it gives people a way to know the primary structure of a protein and then make a prediction about what secondary structural elements form. Is there nothing but alpha helices? Are there any beta sheets? Now, this is a prediction. This is a prediction based on past data, past evidence. Is it guaranteed to be right? No, not at all. But this is certainly a step in the right direction. This gives you a place to start from and say, okay, well, this gives me a P sub alpha of 1.42. Okay, so it's likely that this is going to be an alpha helix. Okay, let's check the next amino acid and the next amino acid. If that alanine is followed by like 5 straight prolines, well, then it's unlikely to form an alpha helix. But if it's an alanine followed by 10 more alanines, there's a pretty good chance that you're going to form an alpha helix there. Now, this Chow-Fastman prediction proposed final secondary structure as the consensus of all amino acids in a region. Okay, so what they basically came up with was a minimum of 4 amino acids out of 6 should show an alpha preference, or 3 out of 5 should show a beta preference, or clusters of 2 to 3 breakers in a sequence of 4 are needed to set the secondary structure in any region. Individual misfits adopt the secondary structure of their neighbors. So if you have 1 or 2 helix preference amino acids scattered in a majority of beta sheet formers, the structure is entirely beta sheet. Okay, so what that means is, let's say that we have a alanine has a P sub alpha 1.42, P sub beta of 0.83. So let's say that we had A, 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 that would be 5 alanines. Those are all alpha helix formers. And then we had something like an aspartic acid, then A. Okay. Now, what this means is that we have 1 or 2 misfits. Here we've got 1 misfit in a majority alpha helix. This is going to form that alpha helix. Now, with that said, we've also got kind of these thresholds. And where it gets complicated is when you're kind of dissecting these things. So a minimum of 4 amino acids out of 6 should show alpha preference. So what that means is that if we've got A, B, E, A, this is 6 amino acids, 4 of which show alpha preference. Since 4 of these show alpha preference, and these 2 right here show beta preference, this is going to form an alpha helix. Now, in order for the tide to shift the other way, for there to be a beta sheet, then let's switch it. We'd say, okay, we'd be looking for D, 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 A, D. That's 5 amino acids. 4 of them happen to be beta sheets. So actually, let's go D, 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 A. There we go. This is 5 amino acids. 3 of them are beta sheets. So essentially what that means is, or one of the ways that you could kind of look at this is that you've got to have 4 out of 6 to show alpha helix, 3 out of 5 to show beta sheet preference. It's almost like the threshold for a beta sheet is going to be a little bit lower, because 4 out of 6, if you divide that out, that's 2/3, that's 66%. whereas 3 out of 5, that's 60%. So you're still at about, the majority of the amino acids in a stretch have to be one or the other in order for something to take place. Now, with all that in mind, you have polypeptides that are alanine, histidine, alanine, or sorry, alpha, beta, alpha, beta, alpha, beta, alpha, beta. You might have a pattern that is so complicated that you're not going to form an alpha helix or a beta sheet. So that's an important thing that you have to keep in mind. You're not necessarily going to form one of these structures. Now, one thing that remains to be true, proline is never at the center of an alpha helix. So that's kind of a takeaway. Now okay, so that's all about our secondary structure. We've got our alpha helices and our beta sheets. Then we have those tight turns where we're either having a proline or a glycine. Now the tertiary structure of a protein. The folding of a polypeptide chain in three-dimensional space is referred to as the tertiary structure. The tertiary structure is concerned with the arrangement in space of all atoms in a polypeptide chain. The conformation of the side chains and prosthetic groups are included as well as the packaging of the helices and the sheets. The formation of the tertiary structure is primarily determined by the interactions of the amino acid side chains with each other and the backbone atoms. So this is our tertiary structure, our 3D structure. Now this 3D structure includes our R group side chains as well as, we haven't really talked about these, but prosthetic groups. This is a newly introduced term. Whenever I hear prosthetic group, I think of someone who has, or think of, you know, um, a person who has a prosthesis. What does that help them do? That helps them carry out a day-to-day function that they otherwise would not be able to do, would not be able of doing. Whether that's like a prosthetic hand or a leg or something like that, that helps them, that assists them. Proteins have the same sort of thing. Prosthetic groups are chemical compounds that basically make an amino or make a protein capable of doing something they otherwise would not be able to do. Now, those prosthetic groups are included in tertiary structure determination. It's it's relatively easy to predict secondary structure. It's much more difficult to predict this tertiary structure. And that's where there's this huge jump. Like, the way that I always like to think about this is kind of with hope and optimism is that back in the 1970s, predicting secondary structure was infinitely difficult. Chow and Fastman did the statistical analysis and came up with these proposed propensity scores, which those scores are continuously being refined. Um, but they came up with a scoring system, and so then all of a sudden people were like, oh, well, I can give this score and these rules. Okay, cool. Now I can predict if a secondary structure forms. Tertiary structure is much more complicated because you have the R groups, you also have prosthetic groups. Prosthetic groups are something that are added after protein's been formed. Now, the next level and kind of your final level of protein structure is the quaternary structure of proteins. Many proteins consist of more than one polypeptide chain. These polypeptide chains have multiple subunits. There are different polypeptide chains. The individual subunits associate in a specific geometry for that protein known as its quaternary structure. Subunits interact through non-covalent interactions. Okay, so think about that. Is this where we have disulfide bonds formed? No, subunits are not going to be connected through disulfide bonds, or it's unlikely they're going to be connected through disulfide bonds. Proteins with more than one subunit are called oligomers or oligomers. Um, and that oligo is kind of like poly. It's just indicating we have multiple subunits, a dimer, trimer, tetramer, pentamer, hexamer, heptamer, octamer, nonamer, decamer. That's where I stopped, 10. Um, I like this figure or this table right here just because it gives a little bit of a spectrum of how large proteins are. And one thing that I want to bring up right here is this one right here, proteinase inhibitor 3. This is 30 amino acids. This has a molecular mass of 3,427 Daltons. This is 30 amino acids, and generally anything less than 50 amino acids is not referred to as a protein, but rather it's referred to as a polypeptide. Um, Now, that's not a hard and fast rule, that's not an absolute rule, but that is a good thing to kind of keep in mind. Um, but then, as you can see, we have some proteins that are as large as 883 amino acids. That's one subunit. And then we have one protein known as titin. It is a monomer. It is 34,350 amino acids. That is one more than 10,000 times the size of that smallest protein, and it's still a monomer. The level of complexity, the number of subunits, there's not a rhyme or reason for, oh, well, if it's this large, it's got to be multiple subunits or anything like that. Proteins fall into two major categories. They either are globular or fibrous proteins. Globular proteins are folded to a more or less spherical shape, whereas fibrous proteins, they have a much more rigid pattern. They contain polypeptides organized approximately parallel along a single axis. All right, well, that wraps up our intro into protein structure.